Yeah, he's talking about Twitch.
Okay, what about now? Okay. Okay. Now you can hear me. Sounds good. Okay, so for those of you on Twitch, hopefully you can hear everything okay. Um, yeah, yeah, I know, Katie. It's part of the game. Um, so we'll do voice chat in um, Discord, or you can do text chat there, um, or you can do text chat on Twitch. Twitch will be lagged behind uh, by maybe a second or two from the live stuff, but otherwise it should work pretty well. Okay, so let me switch here to the Elgato, and let's get to it. So, first off, let me just actually go through and make sure we have everybody that's supposed to be here. Um, yeah, I'll mute myself here so you guys don't hear me twice. Um, okay, my sister has to backseat drive. Okay, so let me turn off the music. Yeah, my sister's backseat screaming here. Okay, so we'll leave that muted for right this instant. Okay, so I just want to make sure we have everybody here. Do we have Ethan Papineau? Monsieur Papineau, ouez-vous? And if you're on Twitch, just in the chat, then you can just type something in there or in the Discord channel. Um, Okay, and then Julius Kruer, we got you here. Looks like you're on Discord. Um, and let's see, Tim Song, Bernardo Sanchez, um, Noels Rosales, Eli Exner, Brandon Mack, Ahmed Megahead. I'm sure I'm mispronouncing that. Um, Julio Alvarez, Connor Thompson, Evan Bowser, who has the coolest last name ever, by the way, and Spencer Phillips. All right, well, so let's get to it, guys. Okay, so we'll the whole point of this class is to for us to sort of learn how to program an autopilot in Kerbal Space Program. So if you've been watching the news recently, you've probably seen SpaceX doing launches and landings. They just blew up a rocket earlier today that they were attempting to launch and then sort of land, but they've gotten pretty good at landing the first stage boosters um, for their Falcon 9 rockets. So what I've built is, let's go in here. How's the audio level? Okay, so in here what I've got is my Falcon 7 rocket, and I called it that because it has 7 engines down here at the bottom. Game is a bit high comparatively. Okay, I'll fix that. Um, so let me come back out. Okay, hopefully that's a little better. We've also got Devin Lucky here. He's Lucky Gamer, class of 1920. Which year was it, Devin? 20. Yeah. Um, and a repeat offender in being in one of my classes. All right, so we've got this rocket that I built. It has 7 engines. 6 of them around the outside are one type of liquid fuel engine, and the one in the middle is if I could get to it, is called a swivel. And the one in the middle can gimbal its thrust and allow us to steer. The 6 around the outside just they can't do that. The ones around the outside are a little bit more powerful, also slightly more efficient, but the one on the inside is allows the rocket to sort of steer itself. Okay, then we got 2 big fuel tanks, some reaction control systems, an antenna, a service bay, and inside here we've got the computer that's going to control this thing. We've also got a some batteries and some monopropellant, which is what we'll use for the reaction control system. And how many of you guys have played Kerbal Space Program before? Um, Anybody? Bueller? Yeah? Well, okay, Devin, you've played it. All right. Well, so if none of the rest of you have played it, then I'll give you kind of a crash course on how this works. So the game simulates rocket physics relatively accurately. I mean, as much as it can be accurate without being like real rocket science. Um, so we'll the the game, sorry, the fuel for the game is, it just calls it liquid fuel, but basically it's RP1 kerosene. And then you have to combine this with an oxidizer, which is usually just liquid oxygen. and in the appropriate ratio, and then that's how the thing works. And then, so most rockets are not a single stage. So this rocket has this big first stage, and then it will jettison the after the fuel in the bottom stage runs out, and then it will carry on with this second stage, which is this thing up here at the top. Okay, so let me fly this thing and kind of let's see how a launch is supposed to work. So I'm going to manually fly it, um, just to give you a sense for how a launch is supposed to work. And then we'll start programming an autopilot. All right, so here we go. So for manually piloting it, I'm going to turn on a stability assist, and then I'm going to throttle the throttle all the way up. And when I hit space, it will ignite all these engines and also release these four clamps that are around the outside, basically holding us in place. And then off we go. Now, so now I'm going to look basically what should our orbit be like. So right now we are here on the planet, which is basically right on the equator, at our space center. And we want to get into an orbit that's basically like one of these white rings. So these white rings are the orbits of two previous test vehicles that I launched in order to test my code. And so we want to end up in an orbit sort of roughly like those. Now, if you look at it, if I want to get from here to the height of the orbit, that actually doesn't take a whole lot of work. The problem is that I would then fall back to the planet. So most of the hard work of getting into orbit is actually not so much getting out of the atmosphere, but moving sideways really, really fast. So, for example, this object that's orbit is going basically 2 kilometers a second. And right now, we are basically going, well, it's not exactly zero because the planet's rotating, but we're basically not moving. So we have to get up, uh, basically um, to an altitude of 200 kilometers or so. And then also we need to get to move this direction at 2 kilometers a second. So that amount that we have to speed up we call delta V for change in velocity. And we just have to get out of the atmosphere and speed up. All right, so let's fly this thing. Okay, so you'll hear the nice rocket noises. So we'll just go straight upwards for a little bit. But then we want to start gently turning towards the east. So what I'm going to do is I'm going to lock the steering to what's called prograde. How is the engine voice compared to my voice? Do I need to turn the volume down anymore? Engine loud. Okay, turn that down a little bit. Okay, hopefully that's a little better. Much better. Okay, great. So we'll just keep basically tilting over and do too much. So if I go into this map view, we can see basically our current trajectory. So the flight path that we're going to follow is this blue line, but because we're still in the atmosphere, there's going to be atmospheric drag, and that's modeled by a mod that I've installed. So we would actually follow this red line, and then we would hit the surface where this little crosshair is when the crosshair is at the end of the point. So as we keep burning, our point of our highest point raises to higher and higher. And on this particular planet, the atmosphere stops at 70 kilometers. So we just need to get our this highest point, this apoapsis, to be larger. Oop. Okay, I just ran out of fuel on the second stage, and so now we got to jettison it and launch the first stage or second stage. So what we're going to be doing is writing code to automate this. And what I'm going to be doing in my class tomorrow is talking about how to write more code that will make that first stage actually fly back and land at the launch site, sort of SpaceX style. But basically, what we have to do is we need to get our apoapsis, the point of highest altitude, we want to get that to, say, 150 kilometers. And once we do that and then get out of the atmosphere, then we'll do one more burn, which is to get us into a sort of circular orbit. Okay, so that's good. Now, what we would need to do is at this point of maximum altitude, we need to speed up so that we don't fall back into the atmosphere. And the amount we need to speed up by is about 500 meters per second. So I'm going to time warp, basically fast forward until we get close to our maximum altitude here. And then go ahead and put out our solar panels while we're at it. And then I'm going to start the burn. And we can see we're going this fast, and we basically need to be going, what, 2 kilometers a second. So we have to speed up, and we'll just wait until this burn is concluded. Okay, and now we are successfully in orbit. Our highest point would be 167 kilometers, and our lowest would be 162. So relatively circular, not perfect, but it'll work. And that's how you get yourself into orbit. Now, what I'm going to do is I'm going to go back to launch. Yeah, this will just take a second. So there are a number of mods for this game that add automation stuff, and one of them is called MechJeb. And if you hit ascent guidance, and let's say that we wanted to get to 150 kilometers, if I engage this autopilot, it will automatically handle everything. And so let me just run that to kind of get started. And um, let's see, why is it not going? Okay, so this automation will look very much like what I did to manually pilot it. It's going to do a vertical ascent for a few hundred meters. We can see that here. It says vertical ascent. And then it's going to start tipping over. And that tipping over to face east is called your gravity turn. Okay, and it's programmed to start the gravity turn when you hit 100 meters per second velocity. And the ascent profile it's going to use will sort of look like this. And so it's going to start to tip the rocket over eastward, um, and then the rest of it will be very much like we we did when we did this manually. Okay, so let me go back to this at launch. And what we're going to do instead is actually program ourselves how to do this. So yeah, Spencer, the second stage also has fuel and it has its own engine. So the second stage engine, there's only one of them on it. It's this big thing, and then it has this little fuel tank. Um, so it's sort of interesting that much of the fuel you have to burn is just to get out of the atmosphere, to get up. And then we also have to spend some of it to speed up. But this engine that's in the second stage, actually, let me go back to the vehicle assembly and I can show you the, sort of the parts here. So the the engines down at the bottom can, if we go over to our engines tab, we can see the ones that I picked. So we're using this 6 of this one, the Reliant engine, okay, and it has basically a maximum thrust in vacuum at 240 kilonewtons. So there's 6 of those. So there's what, 1300 kilonewtons plus the thrust from this guy. Um, so say 1500 kilonewtons. And we need that much thrust in the first stage because we've got all this fuel to haul. And so if we don't thrust more than our weight, then we're not going anywhere. Now, once we get up pretty high in the atmosphere, we don't really have to fight gravity so much. And so for the second stage, I'm using this engine called a Wolfhound, and its properties are, notice that its maximum thrust is only 375 kilonewtons. So much less powerful than our first stage, but it's also way more efficient. And so I would never use that kind of engine at the base first stage. I only want to use it when I get up into the high part of the atmosphere or out of the atmosphere where there's almost no air. Okay. Also, the efficiency is, in a sense, you can measure with this thing called specific impulse. In the menu bar thing, it says engine ISP 70 at sea level and 380 in vacuum. Basically, the higher that number is, the more bang for your buck you get out of fuel. And so 70 is super low, and basically that's about the specific impulse of a an Estes model rocket engine, right? So it's fine for a model rocket, but you're not getting into space with it. Okay, so yeah, most of the fuel um, is in these two big orange tanks, and most of that will be used to just get us up high in the atmosphere and also speed us up a good bit. Then once this we run out of fuel on this one, we dump it and launch, or sorry, light the second stage engine, and using only this much smaller amount of fuel. Um, so basically, yeah, that's the stuff. And then our vessel here is 115 metric tons. So if we think about how much thrust we had, so if we go back to the Reliant, so at sea level that was 200 kilonewtons, there's six of them, so there's 1200 kilonewtons plus, say, another 160, so 1350. If that number was less than 115, then we uh, we wouldn't get off the launch pad. So, all right, Devin, why wouldn't you want the more efficient engine in the atmosphere? Um, Basically, the what we want in the atmosphere, the better efficiency we can get would obviously be good. But what we need in the atmosphere is the more powerful engines because we have to counteract the fact that we weigh 115 tons. Um, and uh, so if we look back at this Wolfhound engine, right, for us to have enough thrust, oops, not that one. Where was it? Here. For us to have enough thrust um, at sea level to get this thing off the ground, at sea level, this thing only provides 70 kilonewtons of thrust. So we would need, what, uh, 10 of these things? 15 of these things? And we can't do that. So, yeah, the better efficiency you can get, great, but we also have to have a positive, or sorry, a thrust weight ratio. Um, uh, yeah, that's bigger than one. So, not exactly, Devon. Does more power always mean less efficient? But often it does, and there's a lot of physics that I'm going to skip over here. So, for example, there is an engine in this thing that has 800 as its efficiency in vacuum, but it only provides 60 kilonewtons of thrust. So, um, yeah, now, we could also put on solid rocket boosters. So, for example, solid boosters, let's find this one, right? So I could strap some of those things onto the side, and those provide a lot of thrust, but they're not particularly efficient. But we used them basically just to get us off the ground. And the biggest one that's in this game is, where is it? They call it the kickback. This would be like the space shuttle's solid rocket booster, and that thing provides 600-ish, um, 600-ish kilonewtons, and then there's this massive thing that provides 1700 kilonewtons, right? So our first stage could just be this thing, um, or one of these uh, gigantic engines like this thing. Um, but the downside to using a solid booster is once you light it, you can't turn it off. Whereas with liquid fuel rockets, you can control the thrust a little bit more. Okay, so that's the rocket. So let's launch this thing and start talking about the programming. Okay, so let me close some of these windows. So we're going to use this thing called the Kerbal operating system, and let me turn the font size down. And this is a mod that basically allows you to put little computers on board, and then you can write programs. So, for example, the finished product for how this will look will be something like this, right? So here's the whole program that I wrote to do the automatic ascent. Why is this go there? goes. Okay, so we've got a bunch of code. Wonderful. Um, so we're going to make a new file here. And right now it doesn't have anything in it. Clip it quick. What do you mean? Um, so, yeah. What do you mean record it, Devin? Like copy and paste it? Well, whatever. Um, so this language, I'll paste the I'll paste the uh, documentation to it here in the Twitch chat. Okay, so that's where the documentation for this thing is, and um, and actually we can just go to it. So let me just open up the documentation. And let's kind of look at it. So it's got a nice tutorial here, which is a quick start for how to do stuff. And basically, what we want to do is just start to look at. Um, so, for example, we can print a countdown. So I'll just copy this in for sake of demonstration. Oops, it's clear screen one word. Okay, so if I run this, so I'll save that file, and then if I run, then all it's going to do is count down from 10 to 0. Okay, and then the program terminates. Okay, that wasn't particularly exciting because, of course, we want our rocket to fly. So what we want to do after we count down 10 seconds is actually launch this thing. So a couple of things I need to do is I need to throttle up. So I'll set that here. And the way that I do this is just say set variable name to value. And this is a little different than in Python or something where I would say something like throttle equals 1. Um, but yeah, so this is how you do it in this language. And that will have the throttle at 100%, but of course we haven't actually done anything. And you'll notice over here on the left that I have the various stages of my rocket. Now, the rocket really only has 3 stages, but if you look in the list, you see 5 things. And the reason is that here in the middle I've got a decoupler, and that's considered a stage on its own. So we can eject the decoupler, that will split the rocket into 2 pieces, and then we can light the second stage engine separately. So we can, if I hit when I was manually flying this, I just hit space to switch, or to, sorry, to stage the rocket. So what I can tell the program to do is stage, and that will do everything. It will activate everything in stage 4 here, which is the bottom stage. It will ignite our 7 engines, and it will also release the 4 launch clamps, and so we'll start flying. If I hit stage again, it would separate my first and second stage from the rocket, which I don't want to do yet. Okay. Now, if we fly this, so let's just run it. Oops. Then it throttled up. It's counting down, and then it'll start flying. Okay, so this language is called CurvoScript. Um, it kind of reminds me a little bit of BASIC, um, and in some other ways it's kind of like Python. There is another mod called KRPC that allows you to control everything with Python, but there's a reason that I chose to use this language instead. Okay, so as this rocket is flying, there's a couple problems. Notice that it's not pointing straight up. It's actually starting to tilt kind of northwards a little bit. So if I look here in the map view, okay, the trajectory is going kind of eastwards, but also it's a little bit off to the north. So that's not good. Basically, the problem is that we haven't told the rocket how to steer itself. It's just on. And it's going to go, so if wind blew it one direction, it would go that direction. That's obviously not what we want. Okay, so let's go back to launch. Okay, so open the thing back up, and then okay, so we haven't told the rocket basically how to steer. Now, we want to go straight upwards for some amount of time until, let's say, we get 1,000 meters off the ground. Okay, so to do that, what I'm going to do is I'm going to set make a variable called mySteer, and it's an object that has heading 90, comma 90. So the first 90 means straight up, and the second 90 means eastwards. That's the heading of east. So now the second number doesn't really matter if we're going straight up. It doesn't matter what our compass bearing is. But since what we want to do is eventually kind of turn eastwards, what I would do is make this first number, like if I made that 45, we would go at a 45-degree angle facing eastward. But just to go straight up, I want this. Okay. And then we want to wait until some condition has taken place. So um, we can do basically this in this language. It has a construct called wait until. What is it we want to be true? We want our ship's altitude to be greater than some number. So let's just say 500 meters. Okay, and then the program will basically pause right there until the altitude is greater than 500 meters, and then we can start turning it eastward. Okay, so I'll say, um, let's put a print in here. The other thing about this language is that basically every statement has to be ended with period. Um, it's kind of like in Java or something, you have to have a semicolon at the end, but hey, I didn't write the language. Okay, so if we run that, this will keep us pointing straight up until, well, it'll keep us pointed straight up forever, and it will pause until the ship's altitude um, is bigger than 500 meters. And then we could say we'll start the gravity turn, which means we want to start tipping eastwards. Okay, now if you notice when I flew this thing, I didn't turn all the way eastward instantly. I kind of gradually moved um, eastward. And so what I want to do is basically make a looping structure that will slowly change this 90 down to 0. And one way that we could do that is I could set a variable, let me call it set number to 90, and then I'll set up a while loop, and actually it's an until loop in this language. So until the number is, say, less than 1, we're going to do something. And I'm going to say um, set oops, my steer to heading num 90, and then I have to add that to. Okay, so then I want to say subtract. Um, I could do something like that. So over a minute and a half, this thing would gradually every second tip 1 degree over. So let's run this and see how it works. Okay, so it says vertical ascent, and we're going to keep going straight up until we hit 500 meters, and then it should start tipping us a little bit eastwards. It doesn't look like we're tipping over. That's not good. Yeah. Okay, so this doesn't work. We're not actually tipping over. Oh, I wonder if I have this back. Oh, that's the problem. Okay, my bad. I had the two numbers backwards. Okay, so the problem was that here it should have been 90 comma num. Okay. Oops. So the first number is the compass heading, and the second number is the vertical. Okay, so go up a few hundred meters, and then we should start tipping eastward. Hopefully I didn't screw it up this time. And there it goes. So it's going really gently, basically 1 degree per second. And see just kind of how it goes. Okay, so that's looking pretty good. And basically, if we look at our, while this thing is flying, the further eastward we tip, basically pushes this apoapsis point further away from us. The closer to vertical we are, raises it. And if we're sloped over, like halfway, then we're partly raising it and partly pushing it away. Okay, and then we should pay attention to our first stage fuel. Okay, so this is probably a little bit too aggressive of a gravity turn. So we'll kind of want to modify it a little bit. Because now we're going a kilometer per second, and we're only 60,000 feet, 20,000 meters up in the air. And so we're having to spend a lot of energy to push against the atmosphere. So there's a couple things, and now the program's terminated, so the autopilot's not, and we just ran out of fuel. Okay, so that was probably a little bit too aggressive of a turn. And so what we can do to our program is we could slow it down. There we basically did 1 degree per second. We could do like 1 degree every 2 seconds or something like that. That probably would have been better. Or we could try and do something a bit more exotic. Okay, so what do you guys think we should do to make this slope over a little better? Any thoughts from the peanut gallery? You guys are being awfully quiet tonight. Those of you guys on Discord. Yeah, longer wait time. Alright, well let's try that, see what happens. Yeah, that's a good idea too. So we started this at 500 meters, but we could say started at 1,000 meters. So let's do the two together and see what happens. And I should turn that down from a 10-second countdown because I'm getting impatient.
But I got an idea. You could maybe try like multiplying it by 3/4 over and over instead of subtracting 1. That way it's fun.
Yes. So multiplying by some constant over and over. Um, Basically, what that would be called is a proportional controller, and that's actually about what I used in the real program. So um, after we test this out, okay. So now we should be starting to tip over. And by the way, while we're waiting for this thing to get kind of up a bit, um, you may notice that if you've played KSP before, the graphics and stuff look a little different than if you just installed it straight off of Steam. I'm using a bunch of graphics mods basically to crank the visual quality up to 11, and it adds the clouds and other stuff like that. So that was deliberate. You may have seen lightning. All right, so let's look at our trajectory here, and that's looking pretty good. So our apoapsis, remember we want to get this out of the atmosphere, which is the atmosphere just magically stops at 70,000 meters or 70 kilometers. And yeah, Devin, I wanted to kind of flex the 3060 and see how she would do. Okay, so it's out of the atmosphere. Okay, so our first stage engine just ran out of fuel, so that's why it stopped. So that was probably a little too aggressive, because now, while we're very high up, or sorry, a little not aggressive enough. Um, so we could basically mess with um, that steering constant. So let's just kind of do that a little bit. So let me go revert back to launch. Let me save what we have. So to make this a little fancier, let's let's keep it the 1,000, and let's set let's set the um, desired apoapsis to be 150,000. So that's the altitude we want to be at. And then let's change this. So rather than just going a constant degree each time, let's basically make this depend on the difference between the current apoapsis and what we want it to be. Okay, so we can do something like, so we're going to get rid of this number, and I'm going to make this until ship apoapsis is greater than target apoapsis. We're going to do something. So we can get rid of the weight. and then we just need to make this, where it says num here, we need to make that a formula that depends on the apoapsis. Okay, so what we can do is we can do something like the difference between the two. So we could do, for example, 90 times, so this would be target apoapsis minus ship apoapsis. So ship colon apoapsis basically gets whatever the current apoapsis value or current altitude of the apoapsis. Now, of course, that's going to change over time, which is why we want to put this in a loop, so this will get executed over and over again. Okay, so what would happen is if the target apoapsis and the ship apoapsis, so let's say that the target apoapsis is 150,000, and right now on the launch pad, the ship apoapsis is 0. Okay, so we want, so that difference would be 150,000, which is obviously really big. So what I'm going to do is I'm going to divide it by the target apoapsis. Okay, so what'll happen is if we're sitting on the launch pad, the difference here would be, so target apoapsis minus ship apoapsis would be 150,000 because we haven't gone anywhere. And then we divide that by 150,000, we get 1, which we multiply by 90. Okay, so on the launch pad, we should be pointing straight up, 90. If we were, if the target apoapsis and the ship apoapsis were the same, then we would have, this difference would be 0, and we would be tilting all the way over at 0. And if we're in between, then we're in between. Okay, so does that kind of make sense? And I need a close parenthesis right here. Does that kind of make sense? So I make it gradually turn over. Question, preguntas, fragen? Now, what do you guys think? Makes good sense? Yeah. Well, so fair point, guys. If you come to Wabash, you're going to be talking a lot more in class. All right, so let's try it out and see how it works. The other thing is let's change our countdown so that it's until it's 5 so that it doesn't take so long. Alright, so let's see how it works. Can I speed up time a little bit? If I speed it up too much, then the physics, the ship will fly apart. So I'll speed it up to a factor of 2. Okay, so we just started the gravity turn, so we should start to see it tipping eastwards here. And at first it's going to be pretty gradual. Okay, so if we look at, I'm actually going to open up other mods info panel. So we can see what our apoapsis is, 4 kilometers, right, and we're at 3 kilometers. So go into this view, and let's watch our trajectory. Yeah, it would just fly apart. If you run it at four times time, then the physics engine gets confused, and it in Kerbal Space Program world we refer to this as the Kraken, and it destroys many ships. All right, so let's look back at our trajectory. All right, so this looks kind of like what we had before. It's not aggressive enough. But it's kind of working. So as we approach 75,000, we should be at a 45-degree angle right now, okay? And as this apoapsis approaches 150,000, we should be tilting all the way over to 0. So let's kind of see. Yeah, okay, so our first stage is burnt out, so let me eject that and keep going. So this other sort of dark gray line, that's the trajectory that the first stage booster will fly along until it hits the, basically splashes into the ocean. And the apoapsis is going up, but it's going up a lot more slowly because we're now using the second stage engine, which, while is efficient, it's not particularly powerful. Okay, so we've now reached 73,000 meters. We're out of the atmosphere. Okay, so if we were trying to like launch a nuclear weapon or something, this would be a pretty good trajectory. Okay, so program terminated, and oops, should have turned the engine off. Okay, so let's go back to the launch. So yeah, that's the basic idea here. I should have turned the engine off when we got to when our apoapsis was at the desired value. So let me open up now because we've only got a few minutes left before you guys have to start writing. Um, Let me open up the code that I wrote in advance to do this. Um, so a lot of this is going to look very much similar to what we had. I've named a few variables, different things, but I did only 100 meters of vertical ascent. Okay. Um, and then the other thing I did was I basically wanted, uh, so the point of both this program and the later one that I've written is to recover the first stage booster. So I need to leave some fuel in it after I separate the stages so that I've got fuel for the landing part. Okay. And I just decided I'd say save 1,000 units of liquid fuel. Then what I did was rather than doing the exact difference between the desired altitude and the apoapsis, I did sort of this 2/3, 3/2 thing. And what that meant was that we would be going horizontal when the apoapsis hit 2/3 of its desired value. So when the apoapsis hits 100,000, by that point, I mostly want to be spending my energy going east, not up anymore. And so that's what I did. And when the first stage gets down to 1,000 liquid fuel, then I turn off the engine, wait, separate the stages, throttle the the second stage engine back up, and then um, basically keep burning until the desired or the ship apoapsis is at half of the desired altitude, so that'd be 750,000. Okay, and then once I've got, or not 750,000, 75,000. Once I get the ship apoapsis to 75,000 meters, I'm just going to say point due east, and then keep burning until the ship apoapsis is greater than or equal to what I wanted it to be, which was 150,000. Then turn off the engine, which is called SECO, or you may have noticed I had MECO. Secondary engine cut off 1, main engine cut off 1. This is the lingo that we use. And then wait until we're outside the atmosphere to extend the solar panels, and then it runs another program that does the circularization. So let me run the full thing and show you guys kind of what this can do. So I'm actually going to open up I've got two computers on board. I've got the this one which is in the top stage and this one which is in the bottom stage. And so I'm going to run ascent.ks, and I'm going to close that and shrink this a little bit. Okay, what just happened? Oh no, it crashed. Well, crap. This always happens. Alright, so I managed to crash the program. Yep. No, it's not the graphics card. Okay, so that's kind of lame. Let me switch back to the full webcam view. Alright, so that was unfortunate that it crashed right when I was going to show you the really cool part. But basically, and I'll make a recording of it and put it up on YouTube or something. What happens is it runs very much like a SpaceX launch. So when the rocket gets up and we've got 1,000 units of fuel left, the two stages separate. The top stage automatically keeps going, and the first stage flips around, burns westward until its impact point would be basically next to the Space Center, and then it calculates basically when is the point where I need to start burning the engines in order to slow down, so that at the instant I hit the ground, my velocity is basically zero. So that's what I did. So tomorrow's class, and in fact, I can open up let me just open up the code here. So here's the code that we were writing. These files just live in a directory inside the Kerbal Space Program game directory, so you can edit them in whatever IDE or text editor you want. One thing I wish, and I might have to sit down and do this, is that there was syntax highlighting, but I don't think anybody's made a syntax highlighting scheme for this language. Okay, so this circularization node, let me open that. What that does is it calculates basically at the apoapsis how fast do we need to be going so that we'd be in a circular orbit. And then it makes a maneuver node with that speed up needed, and then it executes it. And so that gets us in that nice circular orbit, and then we're done. Okay, so any questions? Oh, you guys can't see it because I am not on the correct thing. All right, so there's the stuff wrong. Yeah. Um, yeah, exactly. It runs in the game. And so KSP is powered by Unity, that's the engine. And so, yeah, it's running within Unity. Um, and the people who wrote it basically had to, you know, make a whole programming language and then also have an interpreter that runs it in Unity. The other mod that we could have used for this, and it would have been fine for the ascent script, is called KRPC, and there you as we get somebody in the Twitch chat. Um, there sorry, what was I saying? Oh, KRPC, the program runs in the Python interpreter completely separate from KSP, but then there's a little part that runs inside KSP that basically receives messages um, the from Python. The reason I chose not to use that is because for the decent script, uh, it doesn't have a way of interfacing with another mod called the trajectories mod, and the trajectories mod basically does calculations to estimate where would you impact, where would you land, um, taking into account the atmospheric drag. If we were doing this on a moon where there was no atmosphere, then we wouldn't have to worry about that. But if I want to do landing calculations on the planet, well, then I need to take into account the atmosphere, and that's not trivial to do so. Okay, so any questions, comments, thoughts? Are you guys all going to run out and buy Kerbal Space Program now? Hopefully, it's on Steam, a Steam sale or something. No? Okay, so let me have to give you guys the link to where the whole essay thing is. All right, so I'm going to put this. Yeah, no money. Um, Trust me though, wait for it to go on a Steam sale and then buy it and its expansion. It's worth every penny. In fact, I think I can get keys off of Humble Bundle or something. If anybody wants a copy of it, I'd be happy to provide. Um, okay, so let me paste this in. Let's see, copy link address, and then in the Twitch chat. Oh, let's do this in Discord. Okay, so in the Discord channel, the perspectives channel, I just pasted um, a link to the essay. Um, and I'll paste this in Twitch too here in just a second. Yeah, so if you guys have played Simple Planes or Simple Rockets, I think there's an iOS game called Simple Rockets. It is um, not nearly as detailed as KSP. KSP is pretty awesome. And there's going to be a second uh, version, so Kerbal Space Program 2 is supposed to come out next year, 2022, something like that. In which case I'll start using it. Okay, so paste this in. In the Twitch chat, you should guys see a bit.ly link, and this goes to um, the Microsoft form for where the whole essay thing is. Um, so basically, you'll put in your info, and then so let me switch back over just so everybody can see it. So this is what you'll see. Put in your name and your email address, the stuff, all the usual stuff with admissions. Then select your topic. So we, of course, I'm Professor McKinney, programming an autopilot and Kerbal Space Program. So just pick that one. This was Thursday evening. And then here's the prompt, basically. Um, Reflect on your reaction to the class session activity and explain what you will take away as the most relevant thing you learned about the main topic, which in our case was a very brief crash course on orbital mechanics and autopilots. Um, yeah, so you guys can use Microsoft Word. Um, or just type it straight in here. It's probably better to do it in Word because then, if you accidentally close the window, you won't lose everything. And then just paste it in there. So I'll kind of hang out here with you guys for the next half an hour or so while you work on writing. And then just when you're done, hit submit. And then this weekend, I get the joyous task of reading these. So I hope you guys enjoyed the session. Um, if you've got questions, you guys are welcome to hang out on the Discord server. You guys probably noticed that there's a lot of channels in there because I've been using it for all of my classes since March when we had to go do this whole online nonsense. And I've been Twitch casting basically all of my classes, which has been great when somebody's sick or in quarantine. Um, and the recordings for everything we moved to YouTube to the Math and CS Department YouTube page, and you can just Google Wabash Math CS and you'd find it. Um, yeah. All right, so I'll go ahead and stop the stream here, but you guys are welcome to hang out in Discord. Um, so thanks again for coming.